TeleOR is a pioneering real-time telemedicine system designed to address the unique challenges of operating room (OR) scene reconstruction for tele-intervention. The system introduces three innovative approaches: dynamic self-calibration, selective OR reconstruction, and viewport-adaptive transmission. Dynamic self-calibration leverages inherent scene features as reference points for calibration, eliminating the reliance on preset markers or physical calibration tools. This technique enables cameras to move and self-calibrate in real time, effectively avoiding obstructions. Selective OR reconstruction focuses on dynamically changing scene segments to reduce reconstruction complexity, optimizing data transmission based on real-time client feedback. Viewport-adaptive transmission efficiently delivers high-quality 3D reconstructions within bandwidth constraints, making it suitable for remote surgical guidance. The paper discusses the challenges posed by the OR environment, including obstructions from large devices, hanging monitors, and moving staff, leading to frequent occlusions of scene capture cameras. It also highlights the balance between high-quality reconstruction and efficient real-time transmission as significant challenges in surgical tele-intervention. TeleOR's design and insights are critical for overcoming the spatial and technical barriers inherent in remote surgical guidance. Comprehensive experiments on the four-door surgical scene dataset demonstrate the superiority and applicability of TeleOR, illuminating the potential to revolutionize tele-interventions by overcoming the spatial and technical barriers inherent in remote surgical guidance. TeleOR, a real-time remote operating room system, addresses the challenge of reconstructing and transmitting dynamic scenes in resource-constrained environments. By selectively reconstructing crucial areas and transmitting only relevant segments, TeleOR simplifies the reconstruction process and ensures high-quality 3D reconstructions in real time. The system's viewport-adaptive transmission strategy leverages real-time feedback from the client to transmit and render only the viewed segments, making it suitable for underdeveloped regions with limited network bandwidth. Comprehensive evaluation on the four-door dataset demonstrates TeleOR's effectiveness and reliability for tele-intervention applications. Current approaches to operating room reconstruction focus on holistic scene comprehension, integrating sensing technologies to identify individuals, objects, and their interactions. However, they have yet to achieve real-time remote surgical intervention. TeleOR bridges this gap by providing remote professionals with real-time fully immersive teleconsulting capabilities. The proposed methodology integrates multi-view self-calibration, selective OR reconstruction, and viewport-adaptive transmission. Multi-view self-calibration addresses the challenges of real-time OR reconstruction, including obstructions of capture devices and restrictions on pre-recording setups. A dynamic self-calibration strategy exploits features extracted in the OR scene as the calibration reference, ensuring accurate camera positions and alignments. The system's architecture consists of RGB in-depth sequences, multi-view OR reconstruction, synthesis server, optical flow, difference, orb features, viewport trajectory, and predicted future viewport. TeleOR's selective reconstruction and viewport-adaptive transmission enable real-time observation of surgeries, facilitating remote professionals' teleconsulting capabilities. In the context of the TeleOR system, a real-time remote operating room environment is proposed to enhance the efficiency and accuracy of surgical procedures. The system's core functionality relies on the continuous updating of camera positions using an optical flow method, which estimates motion by tracking feature points across frames. This allows for dynamic adjustment of camera calibration parameters, ensuring precise and synchronized scene capture within the OR system. The system also employs a selective OR reconstruction technique that leverages the static nature of many objects in the surgical scene. By detecting motion through optical flow analysis, only the changing parts of the scene are updated, while static elements are reused from previous frames. This approach significantly reduces computational resources and data transmission requirements. To further optimize data transmission, TeleOR utilizes viewport-adaptive transmission. By gathering users' past field of view (FOV) movements, an LSTM network predicts the user's next FOV, enabling strategic synthesis of point clouds solely within the predicted area. This approach ensures efficient bandwidth utilization by transmitting and rendering only the scene segments likely to be in the user's view. A prediction range of 120 degrees is employed to cover a wider area for improved situational awareness and minimize data usage. The system's performance is enhanced by employing a prediction range that extends beyond the typical user's viewing frustum, reducing point cloud density from the center of the predicted FOV. This strategy not only enhances the system's efficiency but also improves the overall quality of the remote operating environment. TeleOR, a real-time remote operating room system, adapts to varying network bandwidth by dynamically adjusting the threshold for selective OR scene reconstruction and reconstructed point cloud density. This approach balances the quality of the point cloud stream against the imperative of maintaining real-time streaming capabilities. In the experimental setup, the system is evaluated on the public 4-door dataset, comprising 6,734 scenes captured by 6 RGBD Connect sensors. The evaluation focuses on reconstruction quality and transmission efficiency. The system is implemented on top of Open3D, with RGBD sequences deployed on 6 edge computing devices connected to a synthesis server via Wi-Fi. A real-time player is built on top of Unity and deployed on a Meta Quest Pro head-mounted display. Reconstruction quality is assessed using the Structural Similarity Index metric, SSIM, and Multiview SSIM, MSSIM, which represents the average SSIM value obtained across multiple predefined viewpoints. Scene reuse ratio, RUS, is adopted to evaluate the effectiveness of utilizing previously reconstructed scene elements in new reconstructions. The results show that under limited network conditions, TeleOR achieves a high RUS, indicating substantial reuse of segments reconstructed from previous frames, thereby reducing the complexity of the reconstruction process. Transmission efficiency is evaluated using 2 metrics: frames per second, FPS, and latency. Despite operating under severely constrained bandwidth conditions, TeleOR maintains a frame rate of 22.7 fps. An ablation study is conducted to explore the effectiveness of TeleOR's key designs, including selective reconstruction and viewport-adaptive strategy. The results show that without these core components, a noticeable drop in FPS can be observed, emphasizing their critical role, especially under poor network conditions. The TeleOR system, introduced in this paper, is designed for enhancing tele-intervention in operating rooms through real-time, high-fidelity scene reconstructions. It integrates dynamic self-calibration, selective reconstruction, and viewport-adaptive transmission to address issues like camera occlusions, scene complexity, and bandwidth constraints. Experiments on the 4-door dataset show exceptional reconstruction accuracy and superior transmission efficiency under strict bandwidth limitations, enabling seamless real-time interventions. The system's architecture is supported by various references, including works on volumetric calibration, augmented reality in neurosurgery, and real-time 3D reconstruction. These references demonstrate the TeleOR's capabilities in addressing complex surgical guidance needs while highlighting future directions for improvement. In the context of telepresence in operating rooms, the TeleOR system has been proposed as a real-time remote operating room that utilizes augmented reality, AR, to enhance surgical procedures. This innovative approach aims to improve the efficiency and accuracy of minimally invasive surgeries by providing surgeons with an immersive and interactive environment. The TeleOR system integrates various technologies such as optical flow estimation, motion tracking, and haptic feedback to create a seamless interface between the surgeon and the surgical site. Optical flow estimation, as described in Yeager's work, is crucial for motion estimation in AR applications. It helps in accurately tracking the movement of instruments and tissues during surgery, allowing for precise control and manipulation. Zorzal et al.'s research on laparoscopy with AR adaptations highlights the potential benefits of integrating AR technology into surgical procedures. By overlaying virtual information onto the real-world surgical field, AR can provide critical anatomical details, guide instrument placement, and enhance the overall visualization of the surgical site. This can significantly reduce complications and improve patient outcomes. The TeleOR system also incorporates haptic feedback, which enables the surgeon to feel tactile sensations from the surgical site, further enhancing the sense of immersion and control. This feature is particularly important for delicate procedures where precise manipulation of tissues is required. Moreover, the system's motion tracking capabilities allow for smooth and precise instrument control, reducing the risk of accidental movements and improving the overall dexterity of the surgeon. This is achieved through advanced algorithms that predict and adjust the motion of the instruments based on the surgeon's hand movements. While the TeleOR system shows promising advancements in the field of telepresence in operating rooms, there are still several challenges and limitations to be addressed. These include issues related to latency, image quality, and the need for further validation studies to ensure the efficacy and safety of the system. Future work in this area could involve refining the AR interface to provide more detailed anatomical information, improving the responsiveness of the haptic feedback, and conducting extensive clinical trials to assess the system's performance in various surgical scenarios.